Okay, good morning. There's this sequences and series packet. It's 22 pages long. It's pretty hard. Let's go over some of it. So far you were assigned only pages 1 and 2, so I think these pages were relatively straightforward, but already in page 2 things start getting difficult. So okay, let's talk about page 1 first. These are all sort of, basic kind of problems, but that doesn't necessarily mean they're easy because, new things are hard. So here we go. We're given some information. The 8th term of some sequence is 25, and the 20th term is 61. This is an arithmetic sequence. Question, what's the first term? Okay, so hopefully this is not too difficult. Here we are at the 8th term, that's 25. Here we are at the 20th term, which is 61, and the question is, how many jumps are there to get from the 8th term to the 20th term? And the answer is 12. Yeah, because just 20 minus 8 is 12. So I have to do 12 of these jumps, and so to get from 25 to 61, whatever the common difference is, which I don't know, I have to do 12 times. Okay, so what do I know? I know that if I start with 25 and add the common difference 12 times, then I get 61. Okay, well now I just do this, right? So that's 36. Yeah. So 12d is 36, and so d is 3. Okay, great. Now that I know what the common difference is, then what do I want? The first term. So to get from the first term to the 8th term, I have to add the common difference 7 times. So 3 needs to get added 7 times to the first term to get the 8th term. And so the first term must be 4. Okay, hopefully that was not too bad. If you're sort of very smart or like doing kind of arithmetic or thinking in your head, you could potentially do a lot of this in your head, especially when the numbers are kind of nice and simple and everything turns out to be an integer. But anyway, this is the kind of strategic, systematic way to do it. Let's keep going. Now we have some geometric sequences. So I think the rest of these problems are kind of like the same, right? So 2, 3, 4, let's just plan things out. These are all geometric. This is geometric, and this is also geometric. Okay, here we go. What do I know? The first term is 2. The second term is 2 to the 3 halves. Okay, that's kind of annoying. And what is the 13th term? That's kind of the question. Okay, well, maybe that's not so hard because what does this sequence look like? It looks like 2 to the 3 halves, kind of, etc. And so what is 2 to the 3 halves? It's just 2 root 2. And if that's true, then it must be, since the sequence is geometric, that I'm multiplying by root 2 each time. And so therefore I've just learned that r is root 2. And if that's the case, then to get to the 13th term, what is the 13th term? It's just the first term, 2, times r 12 times. So that's root 2 to the 12th. If you multiply the first term, 2 by the common ratio 12 times, that will give you the 13th term. Okay, so now I just need to compute this. What is root 2 to the 12th? Well, it's just 2 to the 6th. So this is 2 times 2 to the 6th, which is 2 to the 7th, which is 128, and that's it. Okay, good. 3. This involves a little bit of more sort of careful reasoning, but again, I would classify this as common sense. Like, I don't even really need to teach this to you, basically, but maybe some people, want me to or something. I don't know. So here we go. I have a geometric sequence. The second term is 64. The 5th term is -8. What is the 9th term? How can we do this? Well, I think it's helpful to be like, first term, I don't know what you are. Second term, 64. Third term, don't know. Fourth term, don't know. Fifth term, -8. You don't have to do this kind of thing, but maybe it kind of helps. At least if you do it a couple times on paper, then maybe subsequently you can just do it in your head. But certainly it's true that to get from the second term to the 5th term, I need to multiply by r 3 times. Therefore, I have a little equation here. 64 times r cubed will give me -8. So this is the kind of careful algebraic way. All right, well then what is r cubed? R cubed is -8 over 64, so in other words that's -1/8. And if r cubed is -1/8, then r must be -1/2. And once I know that r is -1/2, then what's the simplest way to find out the ninth term? Well, the ninth term is just going to be the fifth term, but multiplied by r 4 more times. So I'll take the fifth term, which is -8, and I'll multiply the fifth term by r to the fourth. That should give me the ninth term. Okay, so now it's just a matter of doing this. Well, that's negative will get fried by the even number 4, and so this just becomes -8 over 16, and so the overall answer is to this problem is -1/2. Okay, number 4, I think it's just the same thing. Maybe this one's like even easier. The first term is 81, the fourth term is 24. Question, what is the seventh term? Okay, I got this. Well, yeah, so it's like this, right? 81, don't know the second term, don't know the third term, fourth term is 24. So I multiply again by r, 1, 2, 3 times. So 81 times r cubed has to be 24. So maybe this one's slightly more annoying because the numbers are bigger or something like that. But don't despair. Also, it's a really good idea if you are the kind of person who just automatically, as a matter of instinct, reduces your fractions. So because what is 24 over 81 to me, because I'm that kind of kid, this is just screaming out at me that these two numbers are multiples of 3. And so if I divide by 3, I get 8 over 27. Well, if r cubed is 8 over 27, then r is 2/3. And now once I know that r is 2/3, then what's the seventh term? Well, the seventh term is just the fourth term, which is 24 times 2/3 times r to the third power. So if you multiply the fourth term by r 3 more times, you get the seventh term. So okay, now I'm going to figure out what this is. Well, I don't know, what is this? Let's see. Oh man. What is that? That's like 24, so that's like 8 times 3, 24 is, and then that's another 8 in the top, and another basically like 27 in the bottom. So I think that becomes 64 over 9. So that's how you do these kinds of problems. Okay, good. That was the first 4 problems. Let's do the next 3. All of which are kind of similar to each other. Now, I know in the past that I bet half of you, maybe 80%, just found this to be totally fine, but other people perhaps find this kind of problem hard, or at least a little bit challenging, or maybe would like a tip on how to proceed. So, oh man, this board is so terrible. I will get a new one very soon. Number 5. How many? It's just terrible. How many terms are there in the arithmetic sequence 18, 24, to 336? Okay, so we're told this is arithmetic, and we want to just know how many terms are in this series. All right. Well, it's clear that D is 6, and okay. I mean, I think this is just easy, right? Because what do I need to know? Ultimately, what I need to know is 18 plus how many of these 6's does it take to get to 336? So if 336 is the nth term, let me just call this. Let me just think of this as the nth term. And if this is the nth term, then I want to know what n is. Well, to get from 18 to 336, I would have to add 6n minus 1 times. This might strike you as kind of a lame way of doing that. I don't know. This seems good to me. So okay, if you then just subtract 18, you get 318. If you divide by 6, you get 6 goes into 300. 50 times, so that's 53, and n is 54. Alright, that was kind of like an algebra way of doing the problem. You could also just sort of almost do the whole thing in your head, and you could just say, well, let's see, what's the gap between 18 and 336? Well, it's 318. How many sixes does it take me to get from 18 to 336? Therefore, 53 of them. So if I have to add 53 sixes, then that 336 must be the 54th term. I guess it's just the same thing, but this is the sort of careful algebra way of doing it. More 6. Find the number of multiples of 7 between 30 and 300, inclusive. Okay, so how are you supposed to do this? Well, let's start. Find the numbers of multiples of 7 between 30. I'm looking at the numbers. Let's think about it this way. Take the set of numbers 30, 31, 32, all the way to 300, and the question is, how many multiples of 7 are there in this set? Well, all right, just using basic number facts. What's the first multiple of 7, which is in this set? Answer 35. What's the next multiple of 7? Well, 42. What's the next multiple of 7? 49, etc. And we keep on going until the last multiple of 7. Well, is 300 a multiple of 7? Probably not. What's the closest multiple of 7 that I can do in my head? Well, personally, 280, to me, I know is a multiple of 7 because 280 is just 28 times 10, and 28 is a multiple of 7. So if 280 is a multiple of 7, then that's almost 300. So I'm only going to be able to fit 14 more in there, right? Because if I add 21 to 280, that will be 301. That will be a multiple of 7. So, okay, what I'm trying to say here is that the last number is going to be 294. That is a multiple of 7 because it's just going to be 280 and 14. And then that's it. Okay, in other words, this problem 6 just reduces to problem 5, right? The answering the question, how many multiples of 7 are there in this set, just reduces to, hey, here's an arithmetic sequence, 35, 42, 49, all the way to 294. What are the number of terms in this arithmetic sequence? And so I'll solve this problem the same way I did a minute ago. Why not? Let this 294 be the nth term. And so, what do I know? I know that if I start with 35 and add 7 n minus 1 times, then that will give me the nth term. And if the nth term is 294, now I just do a little bit of algebra 1 to find out what n is. Let's see, I subtract 35 from that, so that's 289 minus 30 is 269. Did I do that right? No, not even close. What did I just say? 294 minus 5 is 289 minus 30 is 259. Yeah. And, okay, how many times does 7 go into 259? Well, it better go in, right? Let's see. I don't know why I'm having so much trouble with this. Okay, so that's like 210 and 49. So 70 goes into 210 30 times, and 70 goes into 49 7 times. So that must be 37. Let's just do a quick check. Yeah, 210 and 49. Boom. So that's how you kind of do this problem. All right, so what's n? N is 38. Therefore, 294 is the 38th term of this sequence, and thus there must be 38 numbers which are multiples of 7 in here. Okay, question number 7. How many 3-digit numbers are divisible by 4 and 6? Okay, well, if I want them to be divisible by 4 and 6, and they need to be 3-digit numbers. So now I'm looking at all the numbers that from the set 100, 101, 102, all the way up to 999. Well, what does it mean to be divisible by 4 and 6? If you're divisible by 4 and you're divisible by 6, then it must mean that you have sort of in your prime factorization of your number, you are have 2 2's in your prime factorization, and also sort of a 2 and a 3. Okay, in other words, this is kind of common sense, but maybe it's a little bit subtle. If you're divisible by 4 and 6, then you must be divisible by 12, and vice versa. Every number which is divisible by 4 and 6 is divisible by 12, and every number which is divisible by 12 is divisible by all of the factors of 12, including 4 and 6. So those are sort of the same thing there, which is just another way of saying if you're a multiple of any two numbers, then you are automatically a multiple of the least common multiple of those two numbers. Okay. Therefore, this problem reduces to how many multiples of 12 are there in this set I have here. And okay, I can just solve this problem in the exact same way. What's the first multiple of 12 in this set? I don't think 100 is a multiple of 12. Maybe I don't know these by heart, but maybe I do, because I know my 12 times tables, and 108 is 12 times 9. So I guess the first three-digit number, which is a multiple of 12, is 108. The next one is 120, etc. So I'm adding, in other words, I'm creating this arithmetic sequence. What's the last number, which is a multiple of 12? I mean, I really don't know, actually. Let's see. To be a multiple of 12, you need to be a multiple of 4. Maybe like, I would be surprised if 1,000 was a multiple of 12. Is 996 a multiple of 12? I don't really know the best way to do this, to be honest. I guess I can just look for numbers which are multiples of 4 and also multiples of 6. Yeah, that's a good way of doing it. So I think 996 is, because I think 900 is a multiple of 6, 90 is a multiple of 6, and 6 is a multiple of 6. So I bet this is going to work. 12 goes into 99 8 times. Yeah, 8, yeah. That gives me 96, 36, 3. Okay, so indeed, 996 is a multiple of 12, and that will be the biggest one. Okay, so once again, we're in the same spot. Call this the nth term, and I guess this problem is a little bit, I guess this is not the only way to do this. This is just the first way I'm thinking of doing it. I guess there is a lot of kind of logic and math sort of built into this. Okay, well, if that's the nth term, now I just proceed in the exact same way as before. But maybe the numbers are a little bit bigger. So 108 plus how many 12s are required to get 996? And yeah, if I subtract 108, I guess I get 888. Let's see, did I do that right? And 8 is 96, and yeah. And so now, how many times does 12 go into 888? I could probably avoid this, but I'll just do it anyway. So that's 7, 84, 48, 4. So that's 74. So n minus 1 is 74, and n is therefore 75. So there are 75 terms in this arithmetic sequence, and thus there are 75 three-digit numbers which are divisible by 12. Okay, good. That was page 1 of this packet. Let's do page 2, and already in page 2 we're sort of we've left the domain of kind of, you know, easy, straightforward problems that can be solved without any kind of thinking by, you know, cranking out formulas. Maybe even page 1, you know, required some thinking, but page 2 definitely requires thinking. Okay. So let's do these 4 problems maybe a little bit carefully. Number 8 says, find an arithmetic sequence of integers none of whose terms is divisible by 2, 3, or 7. Maybe I'll just write that out really quick. Find an arithmetic sequence none of whose terms is divisible by 2, 3, or 7. Okay, I've been assigning this problem to 100 students a year for 12 years or something, so I know what it's like to try to to solve this problem, I've worked with students individually one-on-one and walked them through slowly the logic required to come up with this on their own. So I'm not going to spend that much slow, careful time on it, but you really just have to sort of think about this. Like, okay, I have an arithmetic sequence. I don't want any of the numbers of this sequence to be divisible by 2, 3, or 7. Let's take one at a time. I don't want any of the numbers in my arithmetic sequence to be divisible by 2. Okay, so there can be no even numbers anywhere in my sequence. What does an arithmetic sequence look like, but that has no even numbers in it? Well, the first term, I don't really know what the first term is. So maybe I can even be kind of subtle about it and say, okay, I don't know what to say about this first term, but I know it can't be even because, in fact, none of the terms of my arithmetic sequence can be multiples of 2, 3, or 7. So, like I said, focusing just on the can't be a multiple of 2 for a moment, can't be even, then maybe my first term is it has to be odd. So, I don't know, maybe just like 1 or something, because 1 is the first odd number. Alright, well, I wonder what my next term can be. Well, my next term has to be also odd. Okay, so somehow this has to be odd, and then the next term after that has to be odd as well. I need to make sure that all the terms of my sequence are odd, because none of them can be divisible by 2. Well, okay, if I start with an odd number, and every subsequent term of my sequence needs to also be odd, then what can I say about the gaps between terms? Well, if you subtract any two odd numbers from each other, you just get an even number. That's just a fact, right? If you add an odd number to an odd number, you get something even. If you add an even number to an odd number, you get something odd. Therefore, in order to ensure that all of the numbers of my sequence are odd, then I need to both start with an odd number and also skip by an odd number. Okay, and so I realized simply to satisfy the requirement that none of the terms of my sequences is divisible by 2, it must be the case that what I skip by is itself even. That will ensure that every number in this arithmetic sequence is odd. You start odd and you stay odd by adding in even gaps. Okay, well now it's just a matter of generalizing this to the other numbers. What does it mean if I want every term in my sequence to not be divisible by 3? Well, then I better start with something which is not divisible by 3. Well, say 1. 1's not divisible by 3. Now, what do I have to do to ensure that all the rest of my terms of my sequence are not multiples of 3? Well, one way to make sure that none of these numbers is a multiple of 3 is just add 3, right? If I just add 3 to number 1, then I'll get 4. Well, that's not a multiple of 3 because it's 1 more than 3. And if I add 3 again, I get 7. Well, that's not a multiple of 3 either because it's 1 more than 6, which is a multiple of 3. If I add 3 again, I get 10. Well, that's not a multiple of 3 either because it's 1 more than 9, which is a multiple of 3. In other words, to ensure, here now I'm generalizing the plus even, instead, to satisfy the second requirement that my number be not a multiple of 3, then what I want to do is add a multiple of 3. In this case I added 3, but actually starting with a non-multiple of 3 and adding a multiple of 3 will ensure that my sum is not a multiple of 3. That was the key sort of sentence. Okay, I think you hopefully kind of get this now because there's sort of one left to do, which is I want to make sure that my sum is not a multiple of 7. Well, now I'll just kind of say, right, that how am I going to do this? Start with something which is not a multiple of 7, say 1, although there are, of course, lots of numbers. And how do I ensure that none of the numbers in my sequence is a multiple of 7? Well, just add a multiple of 7. So if I just add, some multiple of 7, say, how about 7 itself, well, then that will give me, I guess I shouldn't have erased this. So what did I do? I added 2 or something here. I can't remember. I think I, something like that. And now here, what am I doing? I'm adding, say, 7, right? Which will not be a multiple of 7 now, 8, because it's 1 more than a multiple of 7. Add 7 again, I get 15. That's also not a multiple of 7 because it's 1 more than a multiple of 7. Add 7 again, and you get 22. That's also not a multiple of 7. Okay, so the big picture here is to ensure that none of my terms of my sequence is even, I should start with something that's not even and add something even. To ensure that none of the terms of my sequence is a multiple of 3, I should start with a non-multiple of 3 and skip by a multiple of 3. To ensure that none of the terms of my sequence is a multiple of 7, I need to start with a non-multiple of 7 and add multiples of 7. Okay, and so now, finishing off the problem, if none of my terms of my sequence is divisible by 2, 3, or 7, then that means I need to skip by something which is both a multiple of 2, 3, and 7. So for example, what's a number which is a multiple of 2, 3, and 7? Well, there are an infinite number of them, but the simplest thing to do is to take the LCM, the least common multiple, of 2, 3, and 7, which in this case, since they're all relatively prime, is just the product of them all, which is 42. And so if so here's the answer to this problem. Let me start with a number which is not a multiple of 2, 3, or 7, like 1, and let me add 42. So add 42, add 42, add 42, etc. Let me make sure I didn't make any horrendous algebra mistakes. Yep, add 2, add 2, add 2. Yep. Okay, this will do it. In every stage, I add 42, and therefore, by adding a number which is not a multiple of 2, by skipping by a number which is a multiple of 2, 3, and 7, I sort of preserve the property of my numbers being not multiples of 2, 3, or 7. Of course, this isn't the only answer. You could start with any number that's not a multiple of 2, 3, or 7. So sort of what's the next one? I guess the next one will be 43. Is that just kind of true? No, because like 5 is not a multiple of 2, 3, or 7, for example. Yeah, of course it isn't. And so an alternative answer to this problem would be to just start with 5 and add 42. So this would be another answer. 5, 47, adding 42 to that would give me 89, etc. This is also perfectly legitimate. Another possible answer would be to start with something which is not a multiple of 2, 3, or 7. I guess I could just go to like 11, right? That's not a multiple of 2, 3, or 7. There's nothing that says I have to add 42. I could add another number which is a multiple of 2, 3, and 7, say 84. So if I add 84, that gives me, 95, etc. So these are all, this is the most sort of general, the most general answer to this problem is the set of sequences that have this property are the sequences which begin with numbers which are themselves not multiples of 2, 3, or 7, and in which the common difference is divisible by 2, 3, and 7. In other words, 42 or some multiple of 42. Okay, that was very thorough. The next problem is just the exact same thing with just like one added kind of twist. Number 9 says, find an arithmetic sequence all of whose terms are multiples of 2 and 3, but not multiples of 4 or 5. Okay, maybe this is just hard enough that it's actually is kind of a new challenge. So find an arithmetic sequence, all of whose terms are multiples of 2 and 3, but not multiples of 4 or 5. Right. Well, as we've seen, telling me that it needs to be a multiple of 2 and 3 is equivalent to saying that it must be a multiple of 6. So we're looking for an arithmetic sequence such that every term is a multiple of 6. I'll put a smiley face there because yes, I want every term to be a multiple of 6. But not a multiple of 4 or 5. So I needed to sort of not, okay, so there's no good way to write that, right? It can't be a multiple of 4 or 5. Okay, well, how can I do this? What's a good number which is a multiple of 2 and 3, but not a multiple of 4 or 5? Well, 6, for example. So I think the general principle which we inherit from the previous problem is start with a number that has that property, and then figure out how much you need to skip by. All right, well, 6 has the property of being a multiple of 2 and 3, but not a multiple of 4 and not a multiple of 5. How do I ensure that every subsequent number of my arithmetic sequence also have this property? Well, first of all, since 6 is a multiple of 2 and 3, if I want every other term of my sequence to also be a multiple of 6, then I need to skip by a multiple of 6. So my first observation is whatever I'm skipping by must be a multiple of 6. Okay, therefore every term in my sequence will be a multiple of 6. But I don't want any terms of my sequence to be multiples of 4 or 5. And so just now we're back into the previous problem, right? If I want none of the terms of my sequence to be multiples of 4 or 5, then I need to skip by something which is a multiple of 20. Okay, so I also need it to be true that I'm skipping by multiples of 20 because well, it's just the previous problem kind of over again, right? If I always skip by something which is a multiple of 20, then every single term in my sequence will also not be a multiple of 20 because it will be sort of 6 more than a multiple of 20. Okay, and so what should I skip by, which is both a multiple of 6 and a multiple of 20? Well, basically, I need to be multiple of 2, 3, 4, and 5. And what is the LCM of 2, 3, 4, and 5? So there needs to be a factor of a 2, there needs to be a factor of a 3, there need to be 2 factors of 2, and there needs to be a factor of 5. Well, the LCM is 60. So 60 is a number which is a multiple of 2 and 3 and 4 and 5. It's the smallest such number. And so the simplest answer probably to this sequence is 6, and then I skip by 60. So 66, 126, 186, etc. Skipping by 60 every time. Of course, this is not the only answer. You could also skip by 120 every time. There is no reason why you need to use the least common multiple. You just need to use a common multiple of 6 and 20. If you skip by 120 every time, that will work. And there's no reason why you have to start with some other number which is not a multiple of 2 and 3, and also is a that is a multiple of 2 and 3, but isn't a multiple of 4 or 5. Okay, that was good enough, and then some. Okay, let's do these last two problems. Okay, last two problems. They are both quite interesting. Okay, let's go. Find all right triangles having sides with integer lengths that form an arithmetic sequence. Okay, so what am I looking for? I will already sort of do a lot of the hard work by just translating this problem into like a kind of a math picture. And actually, this is what makes all these kinds of open-ended word problems difficult, is they don't tell you what to do. So you need to think, understand, draw a picture, pick variables. Anytime you're choosing your own variables and constructing your own kind of setup to the problem, is you're doing sort of real mathematics here. So that's a quite terrible right triangle, like really terrible. Try this again. Okay, so here's a right triangle. What am I looking for again? looking for right triangles whose sides have lengths with our integers, but also the sides are in an arithmetic sequence. Okay, well, if the sides of this triangle are supposed to be in an arithmetic sequence, then, okay, this picture is a little bit bad because this looks almost isosceles, but what I want is this kind of situation where, I don't know, there's the longest side of my right triangle, of course, is going to be the hypotenuse. So of the two legs, they're going to be different sides, and one of them is going to have some side length, which is an integer, but the three sides are in arithmetic progression, or form an arithmetic sequence, or part of an arithmetic sequence. In other words, I want this to be a plus d, and this to be a plus 2d. Okay, so this was because I'm experienced and because I've done this problem before, it's just obvious to me that this is how I want to kind of set things up, right? I need to now, I'm sort of now asserting that a is a positive integer, d is a positive integer, and let me find out what a and d must be, such that, you know, from here to here is d, and from here to here is d. Okay, once you're there, maybe now it's just sort of not that hard because there's only really one thing to do now. And notice how it says find all right triangles. So I don't want to just find one right triangle. I want to sort of approve, so to speak, that, well, I want to find every single right triangle which meets this property. Okay, there's only one thing to do governing the relationship between the lengths of the sides of a right triangle, and that is the Pythagorean theorem. So, let's do it. What does the Pythagorean theorem say? It says a squared plus a plus d squared equals a plus 2d squared. Oh, great. Now, I just do some math. So what do I get here? I got a squared plus 2ad plus d squared equals a squared plus 4ad plus 4d squared. Chop. Okay, let's see, what does all this turn out to be? Let's move everything over to one side. Let's move everything over to the right side. I think if I do that correctly, what do I get? I get 3d squared plus 2ad minus a squared equals 0. Let me just double check that. 3d squared minus plus 2a, check. Yep. Okay, so what's up with this? Well, this is now some fact that it must be true that a and d satisfy this equation. What can I do here? Well, hopefully I can just factor this. And yeah, I guess I just can, right? This is going to be 3d a d a, and I get 3d squared plus 3ad minus ad minus a squared. Okay, so solving for d, maybe, it doesn't really matter. What do I know about d? I know 3d minus a is 0, or d plus a is 0, just zero product property. But of course, d can't be negative a, because, you know, that's just kind of, you know, not going to happen, because a and d both need to be positive, so they can't have opposite sign. So that's just garbage. So it must be over here, right? So what do I get? I get that a is 3d. Alright, what does that mean? Going back up here to my picture, I see that the only way for these to be in arithmetic progression is if the term I start with is 3 times the common difference. Okay, so let me now substitute for a. Let me just write next to it kind of like 3d, or maybe might as well just erase, right? If a is 3d, then now it enables me to represent this in terms of a single variable, d, so that's 3d. A is 3d, so that makes this whole thing 4d. And that makes this whole thing, if A is 3D, 5D. And there we go. This problem is over, right? What property must every right triangle have whose terms are in an arithmetic progression? Well, I have just proved that the only way for this to be true is if the three sides of the triangle are in the form 3D, 4D, 5D. In other words, a 3, 4, 5 right triangle has this property. 3, 4, 5, of course, is an arithmetic progression. You may have just seen that immediately. But, in fact, any integer multiple of a 3, 4, 5 triangle will also have that property. Which kind of makes sense, right? Because if you sort of dilate the triangle by some certain scale factor, then all the sides dilate by that same factor. And so, like, say, 6, 8, 10 is also a right triangle. It also has side lengths which are integers. And it's also in an arithmetic progression, where you skip by 2 every time. Okay, so that sort of proves now that I have, by doing it in this organized way, I've sort of proved that this is precisely the set of triangles that meet this property. Okay, last problem. Prove that there are no right triangles having side lengths with integer lengths that form a geometric sequence. Okay, and so now, this is number 11. It's a very similar kind of setup, right? Prove that you can't have a right triangle whose side lengths are integers, but the three sides are in a geometric progression. Okay, in other words, let the short side be A, the next side be AR, and the next side be AR squared, where A is a positive integer and R is a positive integer. Show that this just can't happen. Okay, let's go. What do I know? Only one thing, the Pythagorean theorem, so let's do it. What must be true? That A squared plus AR squared is AR squared squared. Why is this impossible? Let's do some algebra. So I get A squared plus A squared R squared equals A squared R to the fourth. So first of all, it seems that A itself is kind of unnecessary or sort of irrelevant, except for the fact that A has to be an integer. So I can just divide through by A squared, and I get 1 plus R squared equals R to the fourth. And, okay, so what? What if A is an integer, somehow I need to show that R kind of can't be. And yeah, so let's just try to solve this equation. Well, this is a quartic, but it's really like a quadratic, right? This is quadratic in R squared. And in fact, you might have seen this before, this exact equation in a video that was recorded a couple days ago. Because what do you get if you try to do it doesn't factor, but if you try to do the quadratic formula now, what happens? Well, you get negative b, so 1 plus or minus the square root of b squared, so that's 1 minus 4 a, and c is negative 1 all over 2. Okay, this is just 1 plus or minus root 5 over 2. Now, since r squared is positive, and root 5 is bigger than 1, this negative solution is impossible. So the only solution is this one. What is this number 1 plus root 5 over 2? This is phi. So this is this famous irrational number, phi, that we have seen. It's the golden ratio. Okay, well, in fact, what I've just shown is that r, in fact, has to be like the square root of phi. Okay, and this number, which is the square root of phi, is certainly not an integer. It is, in fact, it's actually just irrational. And therefore, if r is irrational, does that prove that that this is impossible? Yes, because this number is an integer, and this number is the product of an integer and an irrational number. And the product of an integer and an irrational number is in fact irrational. And so if a is an integer, then AR can't be an integer, since R itself is irrational. And therefore it's just impossible for the sides of this triangle to all be integers, and also be in a geometric sequence. So that's number 11. Okay, goodbye.